All right, welcome back, guys. So in this video, what we're going to be doing is it's going to be more of a challenging video because we're going to be talking about the hyperparameters that what we're going to have to set. And then in the next video, we're going to talk about hyperparameter tuning so that the parameters that we want to tune to get the best possible model. Don't worry, I'm going to go into hyperparameter tuning more if you don't know what it is exactly. So, but before that, we have to set the hyperparameters on our object detection model. And remember, hyperparameters are the parameters that we set. So it's not something that's learned by the computer. Unless, we're going to get into hyperparameter tuning and we're going to tune hyperparameters. But in this video, we're just setting hyperparameters and not tuning any. So I'm going to say, we're going to define a function, hyperparameters. It's going to take in two inputs. I just want to show you guys that, you can add inputs like this too, or hard code them. I just want you guys to see both ways. So don't worry if that doesn't make sense right now. You're going to understand what I mean once we get into it. So let's start and let's say that the number of classes is going to be equal to 1. Because for me, I am only training my algorithm to detect plastic bags. So that's why I have number of classes 1. The number of training samples is actually, we need to find that out. So go ahead and click on this cell above and click on the plus button. And let's try and get the, how many images we have. Good thing I didn't, delete this folder just yet. But if you have deleted it, don't worry because I'm going to tell you, at least for mine. So for example, let's get the path of one of this. I'm going to say copy path, and let's say import glob, and then I'm going to say glob dot, actually I'm going to say folder equals glob dot glob. Oops. And we're going to add an asterisk here so that it goes over every single image. Oops, I said an asterisk. And then I'm going to set a counter to be equal to 0. And then I'm going to say for I in folder, counter plus equals 1, and then print counter at the end. So we have 898 images to train on. So I'm going to set my number of training examples to be 898. And that actually makes sense. Do you guys remember? So I'm going to add one more cell. 898 divided by 2 is 449. That's exactly how many training images we started out with. And then we did the data augmentation. So, where we added the same image except we flipped it. So that's how we get 898. Awesome. Then here we're going to say OD underscore model. So we're referencing this model here, the object detection model. And we're going to say dot set underscore hyperparameters. And we're going to say the base underscore network is going to be equal to, and I'm going to use the ResNet 50. The other option here is the VGG 16. So this is basically the CNN architecture that you're choosing for your model. So I'm choosing the ResNet because I think they perform better. But feel free to try it with VGG. So now I am going to say, well, first of all, I want this in a little bit. I'm going to say use underscore pre-trained underscore model and we're going to say 1, which means that we want to enable transfer learning. So we don't want to, train everything from scratch, because remember that would take a lot of time. So we want to use the weights, the pre-trained weights of, the ResNet 50, and then we just want to modify it enough so that the final output layer corresponds with our needs and with our data structure and what it needs to classify. So we're keeping the early layers of the convolutional neural network, but we're just tweaking the final parts of it, the dense final few dense layers, because remember we don't need to retrain the, for example, the convolutional layers, because those layers already detect edges, small circles, and those kind of things, which is, it's the same for every image. So we don't need to change that. We only want to change the output, because let's say that this ResNet 50 was trained to detect cars. And we don't want the final result to be cars. So that's why we want to use transfer learning, but we want to tweak the final part of the ResNet 50 so that it would detect our classes instead of the cars. So if you don't know what transfer learning is, I know this was a quick intro, and I really do hope that you know what transfer learning is, because there's so much more to it than what I just attempted to explain. Okay, so now we're going to say that the number of classes is going to be equal to the number of classes, which we have defined over here above. Awesome. Now, epochs is going to be equal to number of epochs. That's coming from the parameter over here. And an epoch basically is the number of times that the algorithm will work through the entire data set. So basically how many times we're passing all the images through the data set. Okay, now we have the LR for learning rate scheduler step, and this is going to be equal to LR underscore steps that we given over here. And the learning rate scheduler steps means that at these epochs, the learning rate will be decreased. So for example, if the LR epochs is equal to, I don't know, 10, 20, and 30, like this, then that means that at epoch 10, at epoch 20, and at epoch 30, we're going to be decreasing the learning rate. And remember, the learning rate is how fast the model should learn, or how fast it should attempt to converge to the global minima. And remember, we're taking the derivative of the cost function and updating the weights accordingly. So if your learning rate is too big, then you might jump over the global minima. And if it's too small, then it might take forever to get to the global minima, or it might even get stuck. And remember, with the chain rule, you have the gradient, the vanishing gradient issue, which happens if your model is deep, so you have a lot of layers, and it has a small learning rate, because that way the chain rule, you're using the chain rule to get the the derivative of every single weight as you go back in the layer. And if your learning rate is really small and you have deep convolutional neural network with a lot of layers, then eventually you're going to have the vanishing gradient issue, where the new step, basically, that learning rate has to take will be close to 0, which is why it will be converging to the global minima very slowly if it's a low learning rate. So I know that was, there's a lot more to this, but I do hope you understand what the learning rate is. So now the LR scheduler rate is going to be equal to 0.1, and this is the ratio to reduce the learning rate. So at the learning rate steps, so from our previous example at 10, 20, and 30, at epoch 10, 20, and 30, it's going to decrease the learning rate by 0.1. And remember, you technically or you tend to want to decrease your learning rate as your training is going on towards the end of it. So you don't want to decrease it at the beginning, because at the beginning you want your algorithm to take large steps to converge quickly towards the global minima. However, if it gets close to the global minima, then we want to slow down and take smaller steps so that we don't jump over the global minima. So if you're training for 100 epochs, then you probably want to have your learning rate scheduler step to be around epoch, I don't know, 60, 90, or 60, 80, and then 95. That's what I would recommend. Awesome. Now we have momentum. And momentum, we're going to be setting that to 0.9. And this is an extension to gradient descent, the algorithm, the optimizer algorithm, the optimizing algorithm that we're going to use to get to the global minima. And it basically what it does, it builds inertia in the direction of the global minima, and it helps to overcome oscillations and noise. So basically it helps gradient descent get out of flat spaces, or basically when the derivatives during the back propagation, when those are close to zero. And it's only applied when the algorithm is SGD, or stochastic gradient descent. It's ignored for other optimizers such as the atom or RMS prop. So we're actually going to be using either SGD or the atom optimizer. So we want this momentum to be kept in. Remember, not for the atom, but for the SGD. And the reason I'm saying it like this is because we're actually, when we set up hyperparameter tuning, the optimizer is going to be one of the parameters. So we want to try out our model with both the SGD algorithm, which is stochastic gradient descent, and with the atom optimizer. So that's why we need the momentum. So basically momentum, learning rate scheduler step, and learning rate scheduler rate are basically means to avoid this issue with deep convolutional neural networks where you have the vanishing gradient issue. So that's why we need the momentum. Like I said, when the gradient gets close to zero, then this momentum will help it overcome it, so it's not converging super slow, which could, not even find the optimal solution ever. So now we're going to say that the weight underscore decay is going to be equal to 0.0005. And this is the weight decay coefficient for the SGD and RMS prop optimizer. And it's a way to prevent overfitting. And by having the weight decay turned on, we're not letting the algorithm rely on any one weight too much that it has learned. Because basically, you can overfit convolutional neural networks easily when they memorize the training data too well. And for example, we don't have dropout here. Dropout is another way to prevent overfitting. With dropout, you just drop random weights. So your algorithm can never really rely on any one weight. So that's one way. And weight decay is another way to prevent the algorithm from overfitting, because with weight decay, you're basically taking away the power of any one weight that becomes too big and too dominant. Because remember, the bigger the weight, the more power it has throughout the neural network. So the bigger the weight, the more it affects the final outcome. And so you don't want your model to be too dependent on any one weight. For example, if your training set to train cars was only on red cars, then you might have a weight that picks up the color red. And so if it sees a blue car in real life, it's not going to detect it as a car because it's thinking that, hey, our, you know, our car must be of the color red because I was trained on it and I always got it right during training because all the images were red. So basically this is what weight decay is doing over here. Then we're going to have the NMS threshold, which is going to be equal to 0.45. And NMS is the non-max suppression threshold. So basically the non-max suppression threshold is an algorithm that removes redundant predictions with low confidences. So basically, if any object that gets detected by our model but has a confidence score of less than 45%, it will be ignored. So this is a good way to, get rid of redundant detections, because if you're training an algorithm and you've trained it and then you leave this non-max suppression at a low rate, then basically it's going to show you, detections with low confidence. So we don't want low confidence detections. This is basically what we're saying over here. Now the image underscore shape is going to be equal to 512. And this is the image size. So the images gets rescaled to a square image with this size. And the recommended value is to be between 300 and 512 pixels. So the smaller the pixel is, then the faster the algorithm will be, because remember, it has to process less pixels and less data, but the less performant and accurate it's going to be. So I'll just keep it at 512. And then the number of training samples is going to be equal to the number of training samples that we defined over here. So you can write out number of training samples, or you can just, put in 898, because that's this value. Oops. Just cleaning up here. Awesome. So now let's run this cell. Cool. And we can say set underscore hyperparameters. And we can say that, we want a total of, 100 epochs. And because remember, it takes two arguments. This is number of epochs and the learning rate steps, which we could say should be, it's a string. It has to be a string. So for the learning rate steps, it has to be a string, and the values between the string are, when it should decrease the learning rate. And this could be 70, 80, 90, 95, because if we have 100 epochs, then it should decrease them over here. And I might actually change this epoch in the future. Before we start the training, I'm just going to leave it here. 100 epochs is oftentimes a good start. Remember, the more epochs you have, the longer it's going to take and the more expensive the training will be, but it will also be more accurate because it goes through the entire data set more times. So if you don't want to spend a lot of money, then I recommend you setting a low epoch number, so it doesn't take too long for your algorithm to train. So I'm just going to run this. Name set hyperparameters is not defined. Did I misspell it? Hyperparam. Yep, I think I did. So I corrected the E, and I'm gonna rerun this cell, and now I'll rerun this. Name OD model is not defined. Oh, okay. So, we have to run this again, but if I run this, it's going to give us more errors because I have to run and import other things. As you can see, Sagemaker is not defined. So I have to go to the cell where I imported Sagemaker over here and rerun that cell. Awesome. Now Sagemaker is imported. Now I can say, actually, I also have to have the image URI because that's the training image we're using. So I'm going to run this as well. Okay, name session is not defined, so I have to come up to where the session over here. So I have to run this cell. Cool. Now I have to run this cell again with the image URI. And now I can run the OD model. S3 output location is not defined. Okay, so I have to run this. Now I can run this. Awesome. Now I can run this. Now I can run this. Number of epochs is not defined. Oh, because this is number of epochs. I misspelled that, sorry. So I have to rerun this again and run this. Awesome, so now we have set the hyperparameters. And so the reason I'm not deleting this end part of it where I, had these issues, because I want you guys to see that, I encounter these issues as well. I have to go back and rerun those cells. So, I make these foolish mistakes. So don't be fooled that I get everything correct on the first try. So I will see you in the next video where we set up hyperparameter tuning.